Let's look at the technology that we use for studying extreme environments, in this case deep sea hydrothermal vents and cold seeps. And there are really two phases to exploring and understanding these environments. First of all, you have to find them, because we're talking about environments that are really quite small. They're like little islands on the ocean floor, and that's at the bottom of a very large and very deep ocean. So phase one is actually just finding these island-like hydrothermal vents and cold seeps. And then once you've found them, then we want to be able to make detailed measurements of the conditions in them. And of course, they're small little patches of habitat where the conditions vary a lot over small spatial scales. And of course, we want to be able to collect samples to analyse as well. So that can be samples of fluids that are coming out of the seabed. That can be geological samples, sediment samples, and of course, samples of the biology that thrives around these environments. So what about that first phase then? Okay, first of all, finding them. Well, let's start with hydrothermal vents. Hydrothermal vents, although they are small and at the bottom of the ocean, they do help us to find them because they are spewing out hot, mineral-rich fluids. And those fluids are different from the surrounding seawater. So if we can detect that plume of vent fluids dispersing away from a vent field, a cluster of hydrothermal vent chimneys, then that can help us to home in on that cluster of chimneys, that particular vent field. So hot fluids coming out of hydrothermal vents, they're hot, they're buoyant, they rise. So there's a buoyant plume that rises up. But they're mixing with seawater as that's happening, okay, and losing that buoyancy. And eventually they become the same buoyancy as the surrounding layer of ocean. And from a buoyant plume, they then start to spread out as what we call a neutrally buoyant plume. And that hot hydrothermal fluid, it's mixing with cold seawater, and mineral particles are precipitating out from the dissolved minerals that are in the vent fluid. So, where you see black smoke, that's the high temperature hydrothermal vents. That smoke, those are mineral precipitate particles. Often copper sulfides typically, then iron sulfides, then iron oxyhydroxides. So if we can detect that mineral particle plume, that can help us to find our hydrothermal vents. So our rising plume eventually becomes neutrally buoyant, it starts to spread out sideways, and then Coriolis, the consequence of the spin of the Earth on its axis, actually it spreads out sideways, it starts to rotate into eddy-like structures. And so what we're trying to do usually is intercept that spreading and gently spinning eddy-like neutrally buoyant plume. And that plume, of course, gets blown around by bottom currents. It might end up getting trapped by topography, running along the sides of mid-ocean ridges, for example. And of course, bottom currents can vary tidally, so it's highly dynamic. So finding the vent plume and mapping it and trying to figure out what's the source of that plume, that's the real challenge in the first phase of studying hydrothermal vents. And the technology we use for that first phase, well, we lower instrument packages below a ship and we do what's called tow-yowing. So we know roughly usually what depth this neutrally buoyant plume is spreading out at. And we basically lower an instrument, the CTD, conductivity, temperature, depth probe, but we put a lot of other sensors on there to find our vent plumes. We lower it through the depth of the neutrally buoyant plume, and then we move the ship along, and we rise it up through the plume, and we lower it, and we kind of do this seesaw kind of profile pattern, and hopefully intercepting the neutrally buoyant plume while we're doing that. Now, what we usually see in terms of signals, it's very rare that we actually see any kind of temperature anomaly. You only actually get a temperature anomaly, a difference in temperature between your plume and the surrounding ocean, actually usually when you're in the buoyant plume, and that means you're right on top of the actual vents themselves. Now that's very, very, very rare. We very rarely actually see that and intercept the buoyant plume. We tend to be intercepting the spreading neutrally buoyant plume, and there isn't really much of a temperature anomaly usually associated by that. It's mixed with bottom seawater at that point. But what we do detect in that neutrally buoyant plume is the particle signal. So we put sensors on our CTD package to detect that. We can have something called a light scattering sensor, and that basically measures backscatter of particles that are in the water, tells us basically if the water is turbid, if there are mineral particles present. That tells us we're intercepting that plume. We can also put an electrochemical sensor on there called an EH sensor that measures the redox conditions of the water as well. So often the particles will tell us that we're in the neutrally buoyant plume, and then if we start to see a redox signal, that tells us we're near to where the buoyant plume is feeding that neutrally buoyant plume, and we're closer to the actual hydrothermal vents. So here's what a plume signal actually looks like. The yellow line that you can see there is the particulate signal, and you can see as you go down through the water column it's fairly constant, and then there's a bulge out, and that's where we're intercepting the neutrally buoyant plume, and then it bulges back in as we drop down through the bottom of the neutrally buoyant dispersing plume. So plume surveying will tell us that we're within maybe 5 to 10 kilometres of a hydrothermal vent somewhere on the seafloor typically. The next challenge then is to find the actual source of that plume, the actual hydrothermal vents on the seabed. And that's quite a jump from that water column signal down to actually where the vents are on the ocean floor. These days we have additional technology that can help us with that next step. So in particular, autonomous underwater vehicles are great for this next step. Where these, of course, are vehicles that are not remotely controlled from the ship. We launch them, they're autonomous, they go out, they fly a survey pattern that we've pre-programmed, they're equipped with sensors, and that can help us to map basically what's beneath our plume to try and find the seafloor source of it. So they can be flying maybe 50 metres off the seabed and mapping seabed features in great detail with multi-beam sonar systems. And if you're going over hydrothermal vents, you will actually see the vent chimneys, in that high resolution seabed map. And if they have sensors on them like the EH sensor, the LSS sensor, detecting the particles and particularly that change in the water chemistry, the redox conditions, well, if you get a big signal in EH and you know you're over a cluster of things that your map shows you are sticking up out of the seabed, they're a few metres high, you can bet that those are the actual hydrothermal vent chimneys. So that helps us basically to pinpoint the source of the plumes on the seafloor. Now, when it comes to cold seeps, finding them is a little bit more tricky. It depends on the nature of the seep. If we're talking about something like a methane seep, where there are potentially gas bubbles being released from the seabed, then we can pick up a plume of those bubbles in a similar way. Now, to do that, we don't lower a CTD and tow it up and down. We can use acoustic techniques. We can basically use the ship's multi-beam echo sounder that we use for mapping the ocean floor from the ship, and we can look at what's called the backscatter, the kind of return signals from things that are in the water column. Not just the signal bouncing off the seabed itself, but the signals we get from whatever's actually up in the water column. And we can see plumes of bubbles in that kind of acoustic signal. And then usually we can pinpoint where those bubble plumes are coming from on the seabed, and we know that that's some sort of methane seep. But it does depend on the type of cold seep. That's only where gas is being released that we can use gas plumes to detect the seafloor source and find that cold seep. But whichever way we're going, we've detected our hydrothermal vent, our cold seep. The next phase, once we've pinpointed it on the seabed, is to get down there so that we can make detailed measurements of conditions and collect actual physical samples. So for that final phase, the actual direct investigation of these environments, well, there we need human-directed deep diving vehicles. And those come in two types. Either human-occupied vehicles that we also call submersibles that carry people inside them, allow us to get into the deep ocean and work in the deep ocean with manipulator arms. We can deploy sensors and instruments. We can use manipulator arms to collect samples as well. And these days, increasingly, remotely operated vehicles. So these are connected to a ship by a cable. We stay on board the ship in a control room, but essentially it's the same. We have manipulator arms for working on the seabed, and cameras as well, of course. Now, these human-directed deep diving vehicles, these are different from autonomous underwater vehicles because they are under our direct control. And that is important in these environments because hydrothermal vents and cold seeps, each set of vents or seeps is a very small area of seabed and often topographically complex, with mineral chimneys if it's hydrothermal vents. Conditions vary a lot within that small space. And autonomous underwater vehicles are very good at mapping, but we need to be able to respond to what we're seeing and finding in order to make most efficient use of the technology and collect the samples and data we need to understand these environments. We need to be able to say directly, what's that over there? Let's make a measurement of that, okay? Oh, I want to collect one of those from over there. It needs to be human-directed technology. The autonomous technology can take us to where we use the human-directed technology more efficiently, but we need that direct human control to work efficiently in these environments. Otherwise, your autonomous vehicle would just map, you'd come back, you'd spot a load of anomalies, you'd have to reprogram it to go down and target the anomalies. Well, that's what our brains do with human-directed control. So when it comes to measuring environmental conditions, collecting samples, we have cameras, okay, which we can use to map very detailed patterns of life. And typically we have parallel lasers that provide a scale in our images so we can get some quantitative data as abundances of animals vary, on very small scale, meter scale sort of zonations as conditions change in these environments. And then we have various samplers as well. So hydrothermal vents, we have things like titanium syringes, which can collect samples of the really, really hot vent fluid before it's mixed with seawater, so we can look at its original undiluted composition. We have push cores, of course, that can collect sediment samples. Those manipulator arms can also be used to pick up anything we're interested in, whether that's rock samples for geology. And we have other tools as well. We have things like what we call the slurp gun, which is basically like an underwater vacuum cleaner, as you can see in this video clip here, which we can use to collect samples of animals. And they go into different chambers that rotate on a carousel, so we can collect different samples from different locations to understand the relationship between what lives where and that variation in environmental conditions. So with all of these tools, we have that technology for studying these extreme environments.